So in our next discussion, we're going to discuss a little bit more about classification of compressible flows and the dimensions measures we use to analyse them, and also how we visualise them. And the visualisation will actually give us an important clue about certain features that are going to be important when we do our analysis. In particular, the fact that a lot of the changes in a compressible flow at high Mach number, which we'll discuss in a minute, characterised by regions where there are very slow changes and very localised in regions where there are very rapid changes in the key state variables. Now, we've met before dimensions measures. Certainly you'll all be familiar with the Reynolds number being defined as the product of a characteristic velocity, characteristic length scale, kinematic viscosity. Now this has dimensions, obviously we're using SI, so this has dimensions meters per second. This has dimensions meters, kinematic viscosity meters squared per second. So the Reynolds number is a dimensionless measure, and it's a characteristic measure in the sense that there are in most flows lots of different Reynolds numbers. So there'll be a Reynolds number associated. We take the kind of standard case of something moving with speed u and size L. Then there's lots of characteristic measures. A characteristic measure could be d could be equal to the size of the object, and big U could equal to the speed of the object. But there are also other Reynolds numbers. There's one associated with the wake. And so if y W is the width of the wake, and delta or u W is the speed in the wake, then we could have a Reynolds number associated with the wake, with d being equal to the wake width and velocity being equal to the velocity in the wake. And obviously in that case the Reynolds number does have the potential of changing with distance. In fact in 3D it decreases with distance, in 2D it tends to be a bit constant. So Reynolds number is a characteristic measure. Mach number is quite different. And it can be defined at every point in space, and you can define a characteristic Mach number as well. So in this particular case, we take a speed of the fluid and of the flow and speed of sound. Our discussion of basic thermodynamics, we know that the speed of sound in a gas is basically gamma RT. It depends mainly on the temperature. And this can be defined at any point in space. So the Mach number, quite different from the Reynolds number, can be defined as a spatial variable. You can define a characteristic variable associated with it as well. So again, if we had something with moving with speed us, we can define a Mach number associated with that movement. And C0 in this particular case will be the value associated with C0 is the kind of speed of sound associated with the unperturbed state upstream. And techniques that we use in engineering is classification, and so we use a combination of two things. We use a continuous, we usually define a variable that gives a continuous classification in terms of the Mach number, and we use a textual way of characterizing the distinct parts to that continuous classification. So Reynolds number, for instance, you'll all be familiar with the fact that the Reynolds number can go from 0 to infinity, and we define parts of this range to be low Reynolds number or viscously dominated, to high Reynolds number or turbulent. Quite distinct types of flows, but nevertheless always associated with a high and in fact the case of Reynolds number infinity may be sometimes just described as inviscid. So we use a characteristic measure and we classify the types of flow processes depending on the Reynolds number. And the same thing is we'll see with the Mach number. We'll see on the next slide. Just give you a heads up. With the Mach number, M or MA, sometimes use MA, infinity, 0, 1, and we define or describe these as being critical or sonic. Something in this region being supersonic, subsonic, and we've got a region around here which we call transonic, hypersonic. You'd probably say Mach number bigger than 5, but for our case probably 3 is okay, but 5 would be hypersonic. Now, why do we use this classification? Well, it turns out that as you in these different regimes, the physics changes quite substantially. We'll get onto that in a minute. And so the way that you would deal or model a turbulent flow is quite different from a laminar flow. For a turbulent flow, a lot of the processes are occurring on scales smaller than you can necessarily resolve computationally. And so we use a whole different computational methodology in order to model these, in order to describe these, in order to understand these quite different from low Reynolds number. And low Reynolds number and high Reynolds number are again very distinct processes occurring. One can be described or analysed using a linear analysis, and the other one it's intrinsically non-linear, which is the added complexity of this problem. So, first step is, how do we visualize these flows? Well, there aren't many methods. You're generally talking about flows that move very, very quickly, so the use of dyes, which are common for slowly moving incompressible flows, don't work. And so what we tend to do is exploit the property that the refractive index changes as density changes, and density changes due to compressibility. Compressibility leads to density change. And so there are a couple of techniques there. They give, one is basically a visualization technique, so that's Shadowgraph. It's relatively easy to set up, and it doesn't give you quantitative information, but it does give you an ability to identify certain flow features. So, and it works on the following principle: is that if we have a point light source or localized light source that goes through a region where there's a density change, then the light rays are deflected due to a change in refractive index, where we have to change due to a change in refractive index. Now, the relationship between refractive index and density is one of linearity, rough linearity, where K is the Glass-Dale constant. And the Shadowgraph works basically with a light source that passes through the region of interest onto a recording surface, or surface on which you're on a camera or a board. And it works on the principle that where there's a change in refractive index, it's able to pick up the second derivative. So it means that if we have a shock where the density is low and becomes high, so this would be our shock, a localized region. Then what will happen is our refractive index will also undergo a similar change. That will be N. So that's not really. and this will have a first derivative, so n, and then we've got n hat, and then we've got a second derivative, and the change in refractive index leads to the accumulation or divergence of the light rays, which leads to bright and darker regions. Now, Shadowgraph works in a way that it picks up the second derivative, where it's and so what we see here, and you can see it immediately as a Shadowgraph, is the fact that at these shocks you see a dark region and a light region next to one another, which is pretty indicative of a Shadowgraph. And that picks up the second derivative. You see it's quite localized, and this gives you some indication, even at this early stage, about the kind of flow features you see in compressible flows. Localized regions of rapid change in flow variables, separated by regions where the gradients are very low. This shows you, this is a Shadowgraph of Mach number 3 at a wedge. We could discuss wedging in the when we look at oblique shocks. And of course what you see here is the formation of this very strong shock, oblique shock, and this kind of thicker turbulent boundary layer, this kind of turbines here you see. The flow is still supersonic on both sides in this particular case. And that's how it works. It's relatively straightforward to set up. Schlieren is much more problematic to set up, but it gives rise to, lets you determine quantitative information. So it's used for measuring density variations. Shadowgraph is just a visualization tool. This works on the principle of what we call a Z-optic setup, where we've got a source, two mirrors, camera, and the critical thing in all of this is setting up a knife edge at the focal point of the camera and the mirror setup. And what happens in this particular case is a change in refractive index leads to the light rays deflecting and not being captured by the camera, leading to regions of darkness. The benefit of this is that you can do a quantitative analysis on it, and you can reconstruct the integrated, because it is integrated, density field in this particular case. Requires quite a lot of careful calibration, but it's nevertheless. So on the right hand side is a left hand side 4 candles, right hand side is a helium jet. I don't know what the configuration is in this particular, but you can see the candles on the left. Now, to give you an idea of how the flow changes with Mach number, we're just going to discuss the case of a flow past a cylinder. Cylinder is an example of a bluff body, and bluff bodies are typically characterized by strong vortex shedding, and because it's bluff, it means the flow can't go through. It's essentially pushed around the side, and we know from your previous analysis that we look at the flow around a cylinder, the flow is speed is typically doubled at the side. This is important when we come to look at critical Reynolds numbers. So left hand side, top left hand side here, we see the flow in a liquid of flow past a cylinder, Mach number of 10,000, Reynolds number of 10,000, so it's turbulent, inertially dominated. Mach numbers 0 to all sense and purposes. And you see the typical flow characteristics of separation at here. We've got a recirculating region. We have continuous shedding of vorticity, giving rise to characteristic von Karman vortex street. I can't see what more we can say about that. I mean, the Reynolds number is pretty high. You can see the instability of the instability on the vortex sheet here. Large pressure variation between the sides and inside the wake gives rise to low pressure here, low P, and this is the real nature of the drag force. Significant lift on this, generally with flow past bluff bodies. You'll always have lift. It'll be non-useful lift because it'll be wobbling from one side to the next, and this is typically about 10% of the total drag. So let's see what happens when the same flow is in a gas, and now we've got a Mach number. The Mach number in this particular case will be the characteristic Mach number. Speed of the flow past the cylinder times divided by the speed of sound upstream. So this is a gas. This is a liquid. So liquid, easy to visualize. The flow field, gas, much more difficult. So in this particular case, the Mach number is 0.5, and we'll see what happens when we queue. So we start to see, for 0.45, we see flow features are pretty similar to what we expect. I suspect this is not a particularly deep channel, because I can see kind of recirculating attached vortex on the front end, which is indicative of its interaction with the holding walls on either side. But what you start to see when the Mach number increases to 0.46 is the vortex structure is completely seems to start to be lost. There's a straightening up of the point of shedding, has moved round to the back. We're starting to see some sharp flow structures in here at the side, and there are two critical things going on. There's the fact that although the Mach number upstream is 0.64, the flow in this particular case, because of the blocking by the channel, means that the average flow in this region is going to be U infinity divided by 1 minus the width of the cylinder over the width of the tank. So there's quite an appreciable blocking effect, which will probably be about 15%. I wouldn't be surprised if the picture of this channel is just slightly beyond the width of the camera. So blocking, so that means the Mach number in the vicinity of the cylinder, purely by blocking, nothing to do with by the cylinder blocking the flow in the channel, is probably about 15%. In addition, as we've said before, if the flow is speed U here, then we typically expect the flow to be twice this for a cylinder. That factor 2 is quite important in the next stage. Next thing is we see the Mach number increase. And now what we start to see, as we saw for the Mach number 0.64, there was a big change, is that although the Mach number is 0.64 upstream, close to the cylinder, it's probably going to be critical. It's going to be Mach number is about 1, which is why we see those changes. As the Mach number increases, we see the formation of a normal shock in this particular case. The loss of the attached wake, and downstream still some turbulent motion. And as the Mach number goes up, now although the Mach number is 0.98 and close to critical here, there's a couple of things to remember. First of all, this is a transient flow. People forget when they take these pictures that actually there's a strong tendency when the flow becomes supercritical or supersonic. In this particular case, the shock has a strong tendency to migrate upstream. So the interpretation of this is not so straightforward. But what we do see in the vicinity is a series of shocks, small little wake at the back. Now let's have a look at the for a sphere, in this particular case, Mach number 1.5. And what we see here is at the front we see this strong bow shock. This is Shadowgraph. You can see light and dark region. And we see this bow shock at the front. We see another weaker shock at the side. There'll be expansion fans here, and this is a turbulent wake. So we see the flow structure changes enormously as the Mach number increases, and we see that the flow is typically characterized by these regions where the flow changes are very, very strong, what we call a shock. There are other weaker flow structures that we see here, less strong, quite important, expansion fans, and we have still a very small wake. Now the absence of vortex shedding doesn't mean that there's no drag. Drag in this particular case is kind of what we called a wave drag due to the shocks. So what we can see, if we look more generally at other kind of supersonic flows, is that the use of bluff bodies and bow shocks are an important feature of lots of these hypersonic vehicles. This is a picture of re-entry aircraft. Usually they go Mach number 20, 25, and the presence of the bow shock is quite important for generating drag on the craft itself, and what it leads to is enormous dissipation of heat. There are advantages in terms of material selection of why that's a good thing to do. And we see at the back, this is an axisymmetric body, so we see the shocks, expansion fan, wake. And so this is an indication so in this particular case, with the projectile going right to left, the frame moving with this, the streamlines will be coming in, and they will be deflected by the body itself. Streamlines cannot go into or away from rigid bodies or sort of walls, and so this is typically the pattern of the streamline. Now I've drawn a kind of 2D case. 3D, the streamlines tend to come together as you move away from the center line, which would be the center line of the body itself. And this is in a case of what we call an oblique shock, and it's oblique because there is an angle between the streamline and the streamline is deflected. So it's not perpendicular, it's deflected, it's not perpendicular to the, first of all, it's not perpendicular to the shock, and secondly, the streamline is deflected by the geometrical constraint of the body being present. So now we have our characterization of Mach number. As we said before, when Mach number is 1, it's sonic. And we've got various classifications. Now, for the full case, where we've got supersonic flows, we need to solve momentum, mass, energy, and state equations all together. And that adds a great deal of complexity. But for Mach number less than 0.3, we just need to solve mass and momentum. So problems that might be occurring on slowly moving things, even though the Mach number seems big, 0.3, we can get a good approximation by assuming the flow is incompressible. And the reason why that occurs is that the Mach number appears as Mach number squared in the momentum equation, and 0.3 squared gives us a value of about 0.1 or 10% in our inertia terms. So that's why it's typically an indication of when we need to solve everything or not. So subsonic, we don't need to solve, or we don't tend to need to include energy equation because there are no shocks, and so we couldn't use an isotropic approximation. So that's why we can use momentum, mass, and state. But obviously, transonic, supersonic, hypersonic, all these things need to be included. And as you see, as the Mach number increases, we start to have to change the design of the craft itself. We start to have to change the shape of the wing, and we start to now have to change what we do with our thrusters. And so here we've got a prop engine for subsonic flows. Obviously we need a jet gas turbine for transonic. The transonic is usually as a consequence of the flow blocking rather than the plane going faster than the speed of sound. It's typically, the speed of sound is typically increased by about the nominal Mach number is probably increased by about 20% by going over the wing. Wings, if you notice on the plane, they tend to be rather thick, smooth at the front, sharp at the back, and this blocking by the aerofoil leads to probably 10%. So a critical Mach number for which you will have transonic flow over the aerofoil might be only about 0.87. The main difference, and we're going to discuss this quite a lot later, but the main difference is we can see immediately when we start to look at the shape of aerofoils, since we're going to be looking at lift and drag later. So the top figure shows a kind of shape of an aerofoil typical for subsonic flows, you'll see on your Ryanair or BA flight. And its lifting surfaces work because they're characterized by two things. First of all, it's just purely geometrical. The front is smooth. Smooth means that the drag is low. And the back is by a sharp edge. And what this does is it fixes the circulation, or it fixes the lift. Now, lift. Now, if we had a sharp front and a sharp back, then we would have drag, quite a lot of drag. It will be shedding like anything, we would have drag. And it wouldn't be an efficient lifting surface. If we had a smooth front and a smooth back, then we would have certainly low drag, but we'd have low lift. And that pinning of the lift at the back, and we've got the potential for the lift fluctuating. That pinning at the back is really a direct consequence of the sharp trailing edge. Now, if we take that surface, very good design, a lot of science has gone into it, and put it on an aircraft that's going supersonically, what will happen is that we'll end up with a bow shock at the front, an enormous drag, and consequently it will just be a bad design. And so to get around that, well, there's not much you can do. You just have to start looking at where you're getting your lift from. So you'll see that with supersonic flows, a lot of the lift is not from the airfoil itself, but from the whole blended wing. Sorry, and we will have a sharp leading edge. For supersonic flows, for the aerofoil shape changes by making the front and leading edge sharp, and what this does is it pins the presence, it eliminates the bow shock and pins the front shock and expansion fan. And this gives rise to lower drag, or low drag. Now, if you do take the aerofoil that runs at subsonic flows and run it close to sonic conditions, in fact this probably has a Mach number, I was saying probably about 0.97, then the flow is slightly faster upstream, and so what you will end up with is shock formation. Then you'll end up with an expansion, and then you'll end up with another shock, and so you'll end up with this series of a series of shocks, and that will interfere with the boundary layer and give rise to vortex shedding. The flow will still be subsonic, and that transition will be through supersonic. Then because the cross-section is decreasing at this stage, it's like the flow expanding, so the Mach number goes up, you'll end up with another shock, and then the formation of the wake means that the flow detaches, and so that expansion stops, and then you ultimately end up with a subsonic flow. This is fast enough that you've got shock formation on top and bottom. Generally, what happens is this kind of disappears. So So maybe that is actually close to, maybe that is at 1. If you're getting shock formation so far away. Generally the shock formation is quite localized for transonic flows. So this kind of shows the difference between subsonic and supersonic flows. The physics changes, you need to pay special attention to the shock formation, which makes it a fascinating area of research.